In this section, we'll look at the application of the developed methodology for FDI of a single stack PEM electrolyzer present in Polytech Lille. Let's explore the setup at Polytech Lille for green hydrogen production. We use solar panels, a wind turbine, batteries, a PLC controller, and single cell PEM electrolyzer. Hydrogen is stored in a metal container. The schematic diagram at the top right shows power flow from photovoltaic panels and wind turbines to a common DC bus. The battery supports two-way power exchange, supplying electricity during shortages and charging during the surplus. For efficient data acquisition, we employ a MATLAB simulating system connected to the PLC system. Now let's explore how we introduced fault in our system. Starting with the real system, we created a symbolic model of the PEM electrolyzer using physics. After obtaining the symbolic model, we performed parameter estimation using least square method, where we obtained a 1 day of training data and fitted the data closely matched the experimental data. After parameter estimation, we built a simulating model where we already know the value of parameter by our least square fitting, a digital twin of the real system. Simulating parameter fault in the real system can be tricky, so we used the simulating model for this case. Introducing sensor faults involved adding biases during data acquisition in the real system, creating a sensor fault dataset. Parametric faults like changes in resistance were added in the simulating model, forming the parametric fault dataset. These two datasets were then combined, giving us a comprehensive set with 10 different fault classes. On this slide, we focus on diagnostic bond graph model for the electrolyzer adapted from Mr. Sumit Sood's paper. We derived 6 analytical redundancy relations leading to a fault signature matrix using structural relations. There are 9 types of faults, 5 parametric and 4 sensor. Analyzing the fault signature matrix, we find 3 structurally isolable faults. While the rest are non-isolable, we showcase the residual response for a temperature sensor fault here. Using the pure LFT bond graph model, we achieved an F1 score of 0.33, which is not very impressive. The next slide details our improved methodology for more effective fault isolation. For a limited time, I am making my priority DM feature absolutely free for all my subscribers. This is your chance to have direct access to me for detailed discussion, advice on your research project, or any other burning question you might have. If it is a quick query, feel free to drop it in the comment box and I'll get back to you as soon as possible. This giveaway is my way of saying thank you for all your support and engagement with the channel. To take advantage, simply click on the link in the description below and use the TopMed platform to connect. To train the AI model, we start by creating a dataset with 6 residual signals for 10 fault classes. We have around 300 samples for most fault classes and larger number for the no fault class. Using a sliding window with a length of 40, we segment the data resulting in 260 samples per fault class. Next, we downsample the no fault and each fault class, maintaining 260 samples per class. For pre-training, 160 samples per fault class are used with n samples randomly selected for fine-tuning. We reserve 100 samples per fault class to evaluate the deep learning model. In the pre-training phase, we use the KH model, where K is our classifier and H is the feature extractor. For fine-tuning, we modify the neural network with 10 neurons in the last layer representing the number of fault classes and softmax activation. It is essential to replace the initial classifier with one due to the change in the task. So now let's discuss the outcome of our proposed method. Initially, using physics-based model with fault signature matrix, we achieved an F1 score of 0.33. Shifting to a purely supervised approach with 8 samples per fault class, we improved to an F1 score of 0.78. The significant breakthrough came with our self-supervised learning method using the same number of training samples, resulting in an exceptional F1 score of 0.93. indicating a substantial enhancement. Now looking at the prediction plots, the first one shows fault class 4 and second fault 9, demonstrating the model's quick identification of faults introduced in an early stage. The final plot shows the evolution in performance with the increase in label data during the fine-tuning phase. Notably, with just 4 samples for fault class, we achieved a F1 score ranging between 0.85 to 0.9. As we increase the training data, there is a corresponding improvement in the performance. In comparing our method with other state-of-the-art methods who use self-supervised learning, we explored three techniques: denoising autoencoder, value imputation and mask estimation, and contrastive learning. The denoising autoencoder pre-trains the model by corrupting input data, aiming to denoise it. Value imputation and mask estimation involves masking parts of the data to predict masked value. In contrastive learning, a Siamese network determines whether a sample belongs to the same class or not. Results show our method excelling in early stages with a limited training sample from 4 to 64, but it is outperformed as the sample size increased by the second method when 90 samples per fault class is used. It is noteworthy that unlike the referenced paper using raw sensor data, we maintained fairness by using the residual signal as input for all the methods. We used the BGXAI method to explain the temperature sensor fault. The AI model predicts the fault type correctly. Not satisfied with just the prediction, we employ the BGXAI module to get more detailed insight. We find during the fault, ARR1 and ARR6 are given more importance by the AI model. Before the fault, left side of the pink region, all residuals have similar importance. So this concludes the application part, and finally we'll see the general conclusion of this thesis. Firstly, we introduced BGCNN approach, integrating the physical system model with deep learning techniques. Our approach enables the isolation of multiple simultaneous faults, a challenge in existing literature. Then we incorporate the self-supervised learning algorithm to leverage unlabeled data. With this proposed method, we achieved impressive F1 score with a minimal amount of labeled data. Furthermore, we utilized the BGXAI method to generate meaningful explanation for the AI predictions. The developed approach was successfully applied to the PEM electrolyzer and limitations in this research. This thesis focuses solely on fault detection, and we totally excluded the part of fault severity estimation or fault tolerance control. Our supervised AI approach may struggle if a fault in the monitored system is not already present in the training data. In complex systems without a predefined mathematical model, this hybrid FDI method might face challenges. So what could be the future research direction? Fault severity estimation and remaining useful life estimation can be one. Application of metric learning can be another avenue for research. Assessment of the robustness of this particular method against multiple external factors can be another future research direction. And thank you. That was all about my PhD thesis.